Good morning, good afternoon, and good evening, everyone. It's a great pleasure to be among you today to give the second part of this CCEM webinar. And I would like to deeply thank Alain, who accepted to join me to share this webinar. And for this, he had to wake up very early in the morning today. So thank you, Alain, for doing so, for joining me. This second part will be very much focusing on only one application after Alain presented all kind of application that can be performed using the Josephson effect. We will focus on only the BIPM on-site Josephson comparison, and I will show you some of the results that were achieved using this exercise and to demonstrate some issues with voltage noise and systematic error that can arise using comparing two primary voltage standards. So to start with, I would like to show you the graph of the 10-volt results of the direct Josephson comparison that started a long time ago. It started at the 1-volt level in 1991. Then it was extended to the 10-volt level in 1994, but the protocol at that time was quite difficult to follow for the NMIs. So we decided in 2004 to really deeply simplify the protocol. And from 2004 up to now, we had 28 participants in this comparison at a 10-volt level, and on this graph, there are three participants for which the results were very quite discrepant compared to the others that you can see on the graph here. But I have to say that for each of these three typical particular comparisons, there were a clear technical explanation that could be found to explain the discrepancy at the time of the comparisons. So if you take the value of the red squares here on the graph, you will have a mean value of 0.68 nanovolts. And if you combine all the uncertainties here, the total combined uncertainty of this comparison would be around 5 nanovolts. So this is a relative agreement of 7 parts in 10 to the 11 among 25 participants. So this slide shows you the evolution in the transportable primary voltage standard that we have been using at the BIPM to carry out this comparison. All the points that you saw on the previous graph were achieved using the so-called conventional arrays based on superconducting insulator, superconducting junctions. And for some years, we have switched now to a much modern system, which is based on a SNS junction technology. And the system is a compact version of the liquid helium NIST system, for which you have the rack here. And the nice thing about this system is that the RF source that we use is a compact synthesizer, which is inserted into the rack of the DC bias that you can see in the picture here. So we have not carried out any official comparison so far with this system, but it's ready to be shipped to any participants that would like to participate in the future. So in the next slide, I'm really going to show you some results that were achieved with this system mostly. And what I'm going to review is to show you some examples covering the following points. The first one would be to illustrate the ground loop effect and in a measurement setup. Then I will review some an example of a frequency, the importance of the frequency stability of the RF source. I will show you some results showing the impact of the input impedance of the nanovoltmeter, which measure the voltage difference between the two standards. I will show you as well some result achieved on a leakage resistance to ground. And I will focus on the bias source today and not extend it to the leakage that can exist also between the two voltage output leads. And finally, I will show you also an example of the importance of the effect of the residual thermoelectromotive forces. So to say that all these type of systematic error and sources of noise are a kind of review that we must go through in order to really push the measurement setup to its metrological limits. So The measurement setup for comparing two primary standards is quite simple. As you can see from this slide, we have the two quantum standards, the BIPM transportable one and the NMI JVS on the left-hand side here. So the basis is to connect the two positive polarities of the two standards together and to place an nanovoltmeter between the two negative polarities to measure the voltage difference between the two. One important requirement for a direct comparison, of course, would be to refer both radio frequency sources that irradiates each array to the same time-based reference. This is due to the physics of the Josephson effect, where the Josephson voltage is a very true frequency to voltage converter. But the point from this very easy measurement setup would be to, after that, to really investigate all the kind of leakage resistance or existing resistance between the potential reference of the measurement setup and the one that can be reached with for other parts of the equipment in the measurement setup. We want to a kind of homogeneity in the measurement setup in order to avoid any leakage current, any noise to affect the results. And we will see that right now with an example. This picture was taken during the on-site comparison we carried out with our colleagues in the Netherlands at NMI VSL. So you can see the BIPM transportable system in the back here, and this is the VSL system in the front. And on the very first measurement we carried out to try to compare the two systems, we ended up with a very large difference. As you can see, 1.2 microvolt at the 10 volt level. But even more than this, or even worse, I would say, this voltage difference was very much repeatable with a very low type A uncertainty. This most of the time indicates that we are facing a problem with the ground loop in a measurement setup or an existing resistance between the potential of the measurement setup and the ground of the earth potential of the mains. And in that case, if you take a look here, you will see that the cables that we were using to disseminate the 10 megahertz reference to the frequency counter that you can see here and here were coming from a metallic pipe that was actually surrounding all the screening room where the measurement was installed. And not only that, but this 10 megahertz reference was distributed to other experiments in the same room, creating a giant ground loop. And in addition to that, we found that there was a 100 ohm difference between the potential that we selected for the reference of the measurement setup and the earth of the mains. So once these two main issues were resolved, we ended up with a very nice agreement between the two standards, as you can see from this graph here. Let's take a look now at the importance of the frequency stability of the source that we use for to irradiate the array. Those results were obtained during a comparison we had with our colleagues in Greece in EIM in 2009, and you can see that the first result that we obtain are quite noisy, so to say, because they oscillate between minus 50 and plus 50 nanovolts. And trying to find the reason of this dispersion of the results, we found out that there was quite a not really precise locking frequency on the EMI system. And for that, we found out that there was one of the piece electronic component of the counter that was not cooled down properly. So as you can see, we had to remove the cover and to cool it down properly. But more than this, we tried to investigate on a better frequency to be used with the EIM system. And for that, we installed the BIPM radio frequency source on the EIM system, and we decided to cover all the frequencies available from this source in order to find which frequency would be which offer the best stability on the voltage for the array. And we decided to select a criteria for that. We decided that the frequency stability criteria would be for the array to remain on the state for 10 seconds, and this for both polarities of the array, the positive and negative one. And from this review, you can see that we ended up with a very large and nice zone here in green, covering 2 gigahertz, where the array was meeting the stability, the frequency, the stability criteria that we selected. And once we decided to bias the array on this region, we could ended up again with a very nice agreement between the two standards. So this slide is to illustrate the impact of the input impedance of the nanovoltmeter, which measure the voltage difference between the two standards. These results were obtained during the comparison we had with our colleagues at CINAM in Mexico back in 2011. At the very beginning, our colleagues at CINAM, they wanted to check the meter that they were using on the basis, a regular basis, to calibrate the secondary voltage standards, the Zeners. So we simply replaced the Zener by the BIPM transportable JVS, just to check what was how far we could go with this simple meter. And you can see that the results were quite nice, and they were actually in very good agreement with the specification of the meter. Starting from that point, we decided to install 2 different digital nanovoltmeter, one after the other, of course. And we started with a Kisley, and those 2 digital meters are commercially available and very can easily be found in NMIs those days. So there is the Kisley 2182 and the HP 34420. And you can see that the spread of the points was much better than with the HP, but for the Kisley, you can notice that there was a kind of systematic error at the -10 nanovolts level compared to the HP. I will come to that point in the next slide, but for now, I just would like to focus on the point where when we have an agreement of that quality with using a digital voltmeter, like it is the case with the HP, there is a second option in the BIPM protocol which allows to go to a detector, a nanovoltmeter, which offers better specification in terms of noise, which is the analog detector EM-N11. This is the so-called option A of the protocol, and for this, the 2 arrays really have to remain on the same step for quite a while, a few seconds, I would say more than 15 to 20 seconds. I would like to remind you that those comparisons were carried out with SIS arrays. So you have to really be careful to be able to remain on the same steps, and it was quite challenging for most of the comparison. But in that case, you can see that we could achieve very nice result using this analog detector. So now, if we come back to this point and try to explain the discrepancy that was observed between the 2 digital nanovoltmeters, we carried out a large number of different experiments. And you don't have to look carefully at all of the data on this graph, but it's just to show you that the basis to investigate on this systematic error was to change the grounding of the measurement setup to different places, either on the CINAM side, so to say, or the BIPM side. And we also tried different type of cables and so on. We tried to reverse the polarity of the detector to see what would be the effect and so on, to try to investigate on this error. But you can see that for most of the experiments, the -10 nanovolt remained all along for all the experiments there. So from that results, the only thing we can conclude is that there is a kind of coupling effect between the input impedance of the nanovoltmeter, and we really know that the input impedance of these 2 digital nanovoltmeter, the HP and the Kisley, are very different, and so they would behave differently depending on the EMI surrounding the measurement setup. And I have to say that it's not always in the same direction. It's not always the Kisley, so to say, which shows a systematic error. In many other comparisons, that was the other way around, where the HP was exhibiting a systematic error, while the Kisley was showing a good agreement between the two standards. Let's move a little bit now for a few slides about the leakage resistance to ground, and I want to focus only on the bias source today. This picture here shows the BIPM transportable system, the second version that we've been using with the SIS units. We have the nice feature about this is that we have a bias, DC bias, which is powered from batteries. So this is one point to avoid any ground loop if the DC bias of the participants is always connected to low side. Even more than this, you can see that from this picture that the cable was even not connected to the top of the probe. So the array is, the DC bias, so to say, is disconnected from the array. There is only the RF source which irradiates the array, and the meter here records the voltage across the array. And you can see that we were on step actually. So this is a nice tool that we'll be using to investigate on a possible leakage to ground from the DC bias of the NMI. Let me show you how we can do that. We are going to follow a protocol that was firstly introduced by IWatch, Barry Wood, and Clark Hamilton in 2009. So the basis is to install the switch across the nanovoltmeter. And we will follow the following steps. The first one would be to short circuit the nanovoltmeter and to close the BIPM bias source to the array. In that case, you can see that the voltage applied to the BIPM array will also be applied directly to the participants. And because we removed the DC bias, because we suspected to introduce a systematic error, so it's removed from the equation, and the voltage of the BIPM array is applied to the participants, pushing the junctions of the array to the same voltage. Once this is done, we just have to remove the switch here and to remove also the BIPM DC bias source, and we will end up with a very simple measurement setup where there is no DC bias anymore. The RF source, of course, are still present, of course, but you won't see them in this DC schematic. But there is only the two arrays with the nanovoltmeter. This tool was very important to investigate possible leakage to ground coming from the DC bias source of the array. Another slide now to show you the importance of the stability of the thermo-electromotive forces. Alain pointed out that it's very important, and this graphs here shows some experimental data where you have the positive polarity of the array here, negative polarity of the array here, measured by the DVM, the nanovoltmeter, and you can see that there is a huge, well, not a considerable evolution of the voltage measured by the nanovoltmeter, and then start to stabilize, oscillating but stabilizing. And if you measure the voltage difference, if you calculate the voltage difference from these readings, you will see that the results are oscillating as well, of course, and the span of the result here in this case is between -10 to +10 nanovolts. And once you aim to the stable of thermo-electromotive forces, there is only, so to say, a kind of linear drift of the forces, and the voltage difference between the two arrays calculated now range between -1 to +1 nanovolts. So you could gain 1 order of magnitude by waiting for the stabilization of the thermal EMF. But on top of that, to achieve such a nice evolution of the thermals, you have to be sure that your dewar is open to atmospheric pressure. And of course, one important point is the quality of the temperature regulation in the lab. So all of this was the purpose of all this was to show you that between the beginning of the comparison and the first result that can be achieved and the end of the comparison, there was most of the time a very large difference and improvement from the technical point of view. That's the reason why we decided to publish 2 results in the KCDB, and you can see that almost all the participants had 2 results. Meaning we put in the KCDB the first preliminary measurements, and then at the end of the comparison, when we have pushed the limits of the measurement setup we have been using, we can also write the final results, which is the best one. So that's at least to show you that the BIPM Onsite comparison was a powerful knowledge transfer exercise, especially to investigate on all the systematic error that I tried to describe during this talk. Let's move now quickly to the PGBs. In the case of the PGBs, there is no way to remove the DC bias from the 2 quantum standards, because from the characteristic you saw that the area has to be constantly biased. And in that case, any leakage to ground coming from the electronics that you use to power to bias the array could lead to a systematic error in the result of a direct comparison. So you have to be much more careful with the leakage resistance to ground compared to the previous conventional arrays. We have investigated this issue at NIST, comparing 2 PGBs directly, and when we wanted to measure the leakage resistance of the bias source, we tried to measure the leakage of each of the cards, of the DAC cards that are part of the DC bias. On the picture, you can see them there. There are 6 cards in total. And of course, every time you add one more card in the chassis, then the value of the resistance will decrease. The leakage resistance will decrease. But now, if you want to plot a model that will explain the evolution of the leakage resistance, if you take only the leakage resistance of each of the card, the model will be the blue one, the blue line here, and won't fit with the experimental data. To fit with the experimental data, you really have to add the leakage resistance of the power supply, which is used to power the electronics that will turn the voltage of the DACs into the current that will flow through the subarrays. So this is to say that you are really to be careful with any part of the DC bias to avoid any systematic error coming from the leakage. And this is to illustrate the importance of the leakage resistance to ground. The point is not to describe all the technical details about this difference in the series that we see in this graph. This data, they were taken from in a direct comparison between 2 PGBs, and you see that the agreement is pretty nice. This is the average value between all of these points here. We have 0.26 nanovolt with a total combined uncertainty of 0.34 nanovolt. But from the uncertainty budget here, you can see that the major contribution of the total combined uncertainty is coming from the leakage resistance to ground. So why do we change the PGB, the transportable system at the BIPM? It's not only to follow the nice evolution of the technology used in Josephson Voltage Standards, so using the PGBs, but also because the PGBs, as Alain mentioned during his talk, offers more application, and one of them is to measure AC voltages from an AC source, the RMS value of an AC signal using the PGBs and the differential sampling technique. So in the past years, we have been trying to push the limits of the measurement setup using this technique to measure different sources in order to extend the current BIPM protocol, on-site protocol, to AC voltages. And this is the occasion for me to really deeply thank all the collaboration with work we had with different NMIs along the years. And that was a very fruitful collaboration because during the last CCEM meeting in 2021, we asked the CCEM to create a task group to review the draft protocol that we have proposed to extend the BIPM on-site comparison from DC to AC using the differential sampling technique. We were very happy to have 12 scientists coming from different NMIs to join this group. And we've been working together to improve the draft protocol. And I'm very happy to tell you that the protocol is now ready since June. And we intend to send a questionnaire very soon to the NMIs to see which NMIs would be interested to participate in the extension of this on-site comparison in AC. And I would like to thank you very much for your attention.